Okay, we're going to look at this example from the book. It's number 57. It's a biology problem. They say a population of bacteria is growing at a rate of, okay, so they call this dp/dt. It's the rate of change of the population, and they give us a formula. Okay, and they say where t is the time in days. So if you tell me how many days this bacteria has been alive in this laboratory situation, I can tell you the rate at which it's growing per day. Okay, that's what this function does. Okay. Now they also tell us that when t is 0, the population is 1,000. Okay, so at the beginning of time, day 0, I guess you could say, the population is 0. Okay, so what we have here is the derivative of the population function, right? That's the rate of change of population. But that information they told us, they said when the time is 0, so at day 0, the population is 1,000. Okay. So look at what they've told us. They've told us the derivative of the population function, its rate of change, and then they told us a specific value of the population function. Okay. Well, if this looks familiar, it's because we've done problems like this already. It's part A is asking us to basically solve a differential equation. They say write an equation that models the population p in terms of t. Okay. So here they gave us the derivative. In fact, we could have just called this, go ahead and call it that now, p prime of t, right? It's the derivative of the population function. And they told us a specific value of the population when t was 0. So the natural question is, well, what is the population function? Okay, we've solved problems like this before. The way we do this, to get started, we know that if we have the derivative of a function, we can find that original function by integrating. Okay, so what we're going to do is integrate the derivative, okay, with respect to t. Okay, so that's the first step. We want to find p of t, the population function after population after a certain number of days. Okay. Well, what I would do here is, again, look at it and maybe you can recognize that this is the rule that we've been talking about in the section. It's going to be a log rule. The variable is t instead of x, but otherwise it's pretty standard. We could start by factoring out that 3,000. Okay, and then when we do that, we'll get 1 over 1 plus 0.25t dt. And remember, what we're trying to do here is get 1 over u du, because then we can use this new rule of integration that we've talked about. Okay. Well, we always call the denominator u. Okay, so 1 plus 0.25t. Okay, that's u. And du in this case, I should say it's going to be the derivative of u with respect to t times dt, okay, instead of du dx times dx, because we're starting with an integral with respect to t. Okay. Well, what is du going to be? Okay. Well, the derivative of 1 plus 0.25t is just 0.25. Okay. So we take that derivative times dt. Okay. So here's what we've got. The integral we're trying to evaluate, it's 3,000, okay, times the integral of 1 over u. And look at what we have here. We've got dt, and we need to have 0.25 dt. Okay. Well, maybe it's helpful to think of it this way, just to make things a little simpler. That's 1/4 dt. Okay. So we just have dt. If we want 1/4 dt, we've got to multiply by a fourth. Okay, right, we just have a dt sitting here at this point. So we can do that as long as we multiply by the reciprocal, which is 4, somewhere else. Okay, so if we do that, we'll factor that 4 outside, and we'll get 4 times 3,000, that's 12,000, times the integral of 1 over u, and times du. Okay, so that's 12,000 times the natural log of the absolute value of u, plus c. And if we go back and look, we need to replace u with what it was chosen to be. It was 1 plus 0.25 t. Okay. Okay, so actually we're not done with part A, but we're really close. What do we know right now? Well, we know almost what the population function is, p of t, right? That's what we're trying to find. Okay, but we don't know this constant c. Now, we did find out, we were told in this problem that when t is 0, the population is going to be 1,000. Okay, So that means when we put 0 into this function, that'd be 12,000 times the natural log of 1 plus 0.25 times 0. Okay, if we put 0 in for t, we better get 1,000. Okay, so what does that mean c has to be? Well, that means that 12,000 times natural log of, well, it's just going to be 1, right? Plus c must be 1,000. Okay. Well, this is natural log of the absolute value of 1, which is the natural log of 1, and that turns out to be 0. Okay, so this whole thing here, well, this is 0, which makes this whole first term 0, and we get c, okay, equals 1,000. Okay, so guess what? Now we know the entire function p of t. 12,000 times natural log of the absolute value of 1 plus 0.25t plus c, which we found has to be 1,000 to match that initial condition. Okay. Alright, so that's the function we were looking for. Okay, now probably, and hopefully, the next two problems aren't going to be as bad, the part B and C. Part B asks, what is the population after 3 days? Well, we've actually done most of the work. We found the population function, so when t is 3, that's 3 days from the starting point. So to find that population in 3 days, we just plug 3 in for t, so we'll have something like 12,000 times natural log of the absolute value of 0.25 times 3. Okay, so put that number inside, take its absolute value, take natural log of that, okay, times 12,000, and then plus 1,000. Okay. Well, this is something you might choose to do in 1 or 2 steps on the calculator, but if you're careful, you can probably type it in all at once. Just to save some time, the expression inside the natural log, you can see is going to be a positive number, so you can just take natural log of this stuff in here. I think it's going to be 1.75. Okay. So I type that into the calculator, and what I get is about 7,715. Okay, I'll round it to the nearest bacteria. Okay, so we can say 7,715, so I guess we would say bacteria cells maybe. Okay, well good, we've answered the first question, and again, it wasn't too bad to answer once we did part A. Okay, well, we were able to find how many bacteria we have after any number of days because we have the population function. Now the second question, or the second follow-up question, is after how many days will the population be 12,000? Okay, this is the more difficult question to ask about a function. What they want to know here is not what's the population in a certain number of days. They want to know when is the population function equal to 12,000. Okay, a little bit more complicated of a question here. But again, we can answer it now because we know the population function. Population function was 12,000 times natural log of 1 plus 0.25t, okay, plus 1,000. And they ask us when will that be equal to 12,000. Okay, so we have to solve this for t. Okay, well, let's see, what can we do here? Well, first of all, we need to get t by itself, so I'll subtract 1,000 from both sides. I probably have to do better than that line. Okay, so let's try it again. There we go, something like that. Okay, so then I get 12,000 natural log of the absolute value, okay, equals 11,000. Okay, to get t by itself, I probably need to divide both sides by 12,000. Okay, get that constant factor to the other side. So I get natural log of the absolute value of 1 plus 0.02, just 0.25 t, and that's equal to 11,000 over 12,000, which I'll just call 11/12. Okay, so now we need to solve for t. Well, again, the nice thing to do here is use that property of exponential functions. If I raise both sides to the power base e, so make this e to the power natural log and e to the power 11/12, e and natural log will cancel in this way. E to a power natural log just gives you the power, 1 plus 0.25t, and that's equal to e to the power 11/12. Okay, well, so how do we solve now? Okay, well, you know, the thing here with the absolute value bars is a little confusing, but you know, remember when we were integrating this function, we talked about the, you know, when we construct an indefinite integral, we're finding the most general function that can have the given expression as a derivative. Do we really need these absolute value bars here? Well, let's examine that. We have something inside. Will this ever be negative? Well, if you look at it, it's only going to be negative if t is negative, and we know we don't take a problem like this and look back in time. I mean, when t is 0, that's the first or the initial day of the experiment, so t is never going to be negative. If there's a solution to this equation, it has to come when everything inside is positive, so we can just erase the bars here. I kind of hate that, but you know, it's really important here that the function we found, we might be able to simplify it in the cases that are practically important. Okay, so this one's actually kind of interesting, though. We can go ahead and solve it now that we got rid of those absolute value bars. If I subtract 1 from both sides, get 0.25t equals e to the power 11/12, okay, minus 1, and then I'll divide both sides by 0.25. Okay, let's see, what do we get here? We get t is approximately, and definitely something we need to find on the calculator. Okay, well, guess what? It turns out to be almost exactly 6. It's like 6.00. Okay, so we can say 6.00 days. Okay, that's how long it takes for the population to be 12,000. I think it's just kind of a coincidence. It turns out to be about 6. It's actually 6.00376. But in any case, that answers the question. After about 6 days, the population will be 12,000.